In this video, we are going to study how we can use EMS for SOLIDWORKS to simulate a planar inductor. Let us take a look at the objectives for this simulation. We will start by extracting some circuit parameters, namely the inductance, the DC and AC resistance. Next, we will get the core loss for the inductor. Then we will get the I squared R loss for the coil. And finally, we will find the temperature distribution in the inductor. We will use EMS for SOLIDWORKS to accomplish all these objectives. Now let us get to EMS for SOLIDWORKS. In this example that you see on the screen, we have a planar inductor. Let me first go ahead and describe all the components that you see in the screen. We will start with a PCB coil here. Next, we also have a PCB in which the coil is actually a trace. We have a core that is made of power ferrite, and finally we have what is called as the outside air geometry. This outside air geometry is very critical and is required for magnetic simulation. Why is that? It is because there is going to be some flux leakage out of the inductor, and to get an accurate solution we would need to capture the value of this leakage flux, and hence you need an outside air geometry. And this outside air geometry is simply a box in SOLIDWORKS which is drawn around the inductor. Now let me go ahead and hide this air geometry. Inside SOLIDWORKS, EMWorks products such as EMS is just an add-in, and you will have the EMS manager where you will organize your EMS simulations. In this particular simulation, we have created what is called as the AC magnetic study. This AC magnetic study properties tell you all the parameters that you wish to gather from this simulation. For example, we have requested the program to compute the circuit parameters, namely the inductance, resistance, etc. We also tell the program what is the frequency of the exciting current. In this case, 1 kilohertz. Finally, EMS has the ability to couple the magnetic simulation to a thermal simulation. Here I have requested the program to compute the steady state temperature distribution in the inductor. We now can look at the various materials that are assigned to the different components. First, the outside air is assigned a material air. And to assign any material in EMS, we can right click and simply select Apply Materials. EMS comes with a predefined material database that allows you to apply materials to your components. All the materials are categorized into common industry categories such as cables, conductor materials, substrates, etc. In this particular example, the core is made of a material called PC95. To study the properties of this PC95 power ferrite core, we can edit its material and you can study its property. You can see the BH curve of this particular material here. Next, we can also take a look at the core loss details of the material, which is given by the Steinmann's core loss function. And all the other material properties are also here. EMS allows users to define their own materials and use them for simulation. The PCB is made of FR4 material, and these are some of the properties of the FR4 material. Mainly, we are interested in its thermal conductivity, specific heat, and mass density. And finally, the coil is made of copper, and this is regular copper material from the EMS database. Once the materials are defined, we next have to define the properties of the coil. EMS allows you to easily define coils. Here, all we need to do is to tell the program where the current enters the coil and where it exits the coil. When we go to the properties of the coil, we can specify what is the RMS value of the voltage that is connected to the coil, and if there are any serial resistances between the coil and the power source, we can denote them in this dialog box. Once the coil has been defined, finally we need to tell the program what is happening between the inductor and the outside ambient air. And to do that, we will define a convection boundary condition. The convection boundary condition in EMS tells you that any surface of the inductor is convecting to the outside ambient with these particular properties, as 10 watt per meter squared Kelvin as the convection coefficient and 300 Kelvin as the ambient temperature. This is all we need to do as far as the inputs to the inductor simulation goes. EMS uses what is called as a finite element method to solve. This method results in the creation of a finite element mesh. EMS uses an optimal mesh setting that is automatically defined for the problem. One can also employ mesh controls to create the mesh. Here you can visualize the mesh generation in EMS. You can see small elements across the thickness of the coil to capture the proximity and the eddy effects of the coil. Next, we can now take a look at the results produced by the simulation. Most of the results that we would like to see are organized inside the result table. Let us recap on some of the objectives that we had for this simulation. We wanted to find the inductance. Now EMS readily gives us the value of the inductance. EMS also gives us the value of the AC resistance. In this case, it is 2.16 milliohm. And you can contrast this with the value of the DC resistance, which is 1.4 milliohm. Notice that the AC resistance at 1000 Hertz is higher than the DC resistance, and it's almost 50% higher. In addition to these data, we can also get the solid loss in the coil, and this is around 0.42 watts. This solid loss in the coil is responsible for the temperature rise in the coil. We can also get the core loss for the power ferrite core. Notice that the core loss at this particular operating condition is not very high. We can also take a look at some of the field results in EMS. I'm going to start by taking a look at the current density plot in the coil. Notice here that you can get a vector plot of the current density. You can also say from the color of these vectors that the currents tend to cling to the inner layer of the coil. You can also see areas in the coil where there is no current. So this helps you to visualize how the current is distributed in the coil. Next, we will take a look at the magnetic flux density, the section plot, so that we can understand the magnetic flux distribution in the model. Here is a section plot of the magnetic flux density. Notice regions of high magnetic flux denoted by red and regions of lower one denoted by green and blue. This plot also helps us to visualize if the inductor is getting close to saturation or not. The red regions certainly show regions which are close or about to saturate in the inductor core. Finally, we will take a look at the temperature distribution. This plot gives you the temperature distribution in the coil and in the PCB. Notice the distribution of the temperature, which is high in the inner regions of the coil, and as we move outside, the temperature reduces. Nevertheless, the temperature rise was not high, and the maximum temperature attained in the coil is only 30 degrees centigrade. One can also study the temperature distribution in the core, and you can see the majority of the temperature rise in the core happens where it is in contact with the PCB. As a recap, we saw how EMS for SOLIDWORKS can help us understand the planar inductor. Namely, we can get the inductance, the AC resistance, the DC resistance, the solid losses, etc. One can also view the field plots, namely the magnetic flux density, the current density in the coil, and finally the temperature distribution in the inductor.